Welcome. I'll talk about approximating weighted connectivity augmentation below factor 2. This is joint work with Vera Traub. So let me introduce the problem. So the weighted connectivity augmentation problem is a very basic network design problem where you're given an undirected graph, which is shown here in black, together with candidate edges shown as dashed blue lines. And I will call them links just to distinguish them from the edges. And those links, they have non-negative costs. And your task is to add a cheapest set of links to your graph to augment its edge connectivity by at least one unit. So let's look at this example. Here's a graph that's 4 edge connected. So one way to see doesn't have a higher connectivity than 4 is by observing that here's a 4 cut, a cut containing 4 black edges. Here's another one. And so what's the goal to increase the edge connectivity? Actually, you can use Menger theorem to observe that increasing the edge connectivity is, of course, the same as increasing the min cut of your graph. So the task is really to find a subset, a cheapest set of links that will cross each of the min cuts of this graph. In this case, each of the 4 cuts. So the first observation, it turns out that weighted connectivity augmentation can be reduced to the ring case. So one can assume that the given graph, the black graph, is just one cycle. And this can be obtained by using results on the representation of min cuts by cacti, and then by some simple transformation. So from now on, let's assume that, and this reduction is approximation preserving. So let's assume that we're given from now on a graph that is just a ring. So what has been known previously, there's been significant work on this and related problems. Actually, one can get 2 approximations through a variety of techniques. This includes specialized techniques, but also banal standard techniques like pi-module algorithms or iterative rounding. Moreover, there's been progress to beat the factor of 2. So factor 2 is kind of very easy to obtain. However, beating factor 2 proved to be very difficult, even for special cases. And one of the most famous special cases is the unweighted tree augmentation problem, which is just a special case where the underlying graph is a spanning tree, and moreover, it's unweighted, which means that the costs are all unit. So you have to minimize the number of links you add to increase the edge connectivity of your graph. In this case, you want to make the tree 2 edge connected. There's been recent progress on the weighted version of tree augmentation, where factor below 2 was obtained. And also parts of this work are inspired by that line of work, even though we have quite a few additional hurdles to overcome here in connectivity augmentation. And also very recently, there's been first below 2 approximations for the unweighted version of connectivity augmentation, where all the links have cost 1. But this work is the first one to beat factor 2 for the general weighted connectivity augmentation problem. So the result we obtain is a 1.5+epsilon approximation. So I think that there's a few ingredients that are interesting. So mostly there's like structural technical ingredients that are of interest, and then they can be used in different ways to beat factor 2. And I'll actually in this talk mostly talk about one simple way to beat the factor 2 that will not yet reach the 1.5+epsilon approximation, but should show the ideas and will also help you understand why one can obtain better than 2 approximations and also get closer to this 1.5 bound. Let me start with a bird's eye view on the approach. So what we're actually going to do is we're introducing a related problem, which we call the directed weighted ring augmentation problem, or directed WRAP. So it's a slightly different setting where links have directions, and we will first solve that problem, which will lead to a solution that can be interpreted as a 2 approximation of the original problem. And then we will try to replace parts of that solution by undirected links that are cheaper. So it'll be exchange step that make this solution cheaper over time. So starting with 2 approximation, you only have to show that we can win a small constant factor that then beat factor 2 in this way. So that's a typical relative greedy way of thinking about things. And that's just one way to nicely illustrate how our techniques can be put into action, but it's not the only way to use them. So as I said, we'll start with a 2 approximation that will be highly structured and then improve on that approximation step by step. So what is directed WRAP? So directed WRAP is a highly structured simplification of the ring augmentation problem. So the main difference is the following between directed WRAP and the ring augmentation problem that you've seen it. So the links are directed, as shown here. And so it's a ring. So we have, as we discussed at the beginning, so our task is to cover all min cuts in the augmentation problem. Here, the min cuts of a ring are precisely the 2 cuts, and they correspond to, we draw 1 2 cut here to such intervals along the ring. And by the way, whenever I draw a 2 cut, I will always draw it in a way that it does not include one specific vertex, an arbitrary vertex, a fixed level called the root, because I mean, a vertex set and its complement and define the same cut, and I want to get rid of that potential ambiguity and always use only those sets as 2 cuts. So in the undirected version, every 2 cut has to be crossed by a link. In a directed version, we require that at least one directed link is actually entering the 2 cut. So if you look at this 2 cut here, then there's, for example, one link that's leaving, so that one is not covering the 2 cut. But there are also 2 links here that are entering, one over here and one here. So these links, they do cover the 2 cut. And also our goal is to pick, to select a min cost set of directed links that will cover all 2 cuts. That's the directed version. What's good to know about it is that it can be solved efficiently. But of course, it doesn't really capture the original problem, which is an NP or an APX hard problem. Just to get a better feeling of the directed version, and also to understand how we start with why we start with a 2 approximation, a directed 2 approximation. So one way, let's just try to get a 2 approximation for another one for the weighted ring augmentation problem. So the original one that is undirected. So assume that's our instance here in the first picture. So just I don't show the weights or the costs, just to make the picture more cleaner. So what you can do is you can first just bidirect each one of the links. So that link here becomes these 2 links over here, and assign to the directed links the same. Each one of them gets the same cost as the link it stems from. Now we have a directed WRAP problem, and this we can solve optimally. That is our solution. That's the one we return. So now when we return that one, so we're returning a link just means we return the original undirected link. So in this case, one can easily observe there must be a solution, and moreover, it must be a 2 approximation, simply because if you look at an optimal undirected solution, then you can just bidirect that one and you have a directed solution of cost twice the opt solution, the optimal undirected solution. So this will lead to a 2 approximation. Moreover, we can actually get a much more structured 2 approximation that way. So what one can do is one can observe that in the directed setting, if you look, for example, here at the orange link, so that link can be, we can actually replace links sometimes by what we call shortenings. So there are weaker versions, this is a weaker version of a link. So in this case, I can replace the orange link by that orange link here, and actually still get a solution if I would do this here in that setting. So what is a shortening? A shortening is simply any other directed link that covers a subset of the 2 cuts of that link here. So again, I recall a 2 cut always is a subset of the vertices that does not contain the ring. Of course, that's precisely 2 black hatches crossing. So as an example, if I look at a 2 cut and say this one here, so that one here is covered by this link, but it's not covered by shortening. The shortening has also the tail in the 2 cut. So it's indeed a weaker version of what was observed, that there's no 2 cut that's covered by shortened link and not by the original. So the idea is to be actually, from the 2 approximation obtained beforehand, we can shorten links, and if we do so, we get a very, very structured solution. And we call the solutions non-shortenable solutions. And they have the following properties. First, it's an R arborescence. Also, it has a planar canonical straight line embedding. So it means simply if you draw the circle in the obvious the convex planar way as shown here, and then you can simply, if you can simply draw the directed links as straight lines, there will be a planar graph together with the circle. And moreover, for every vertex, so a vertex here, you've at most 2 outgoing links. And if you have 2 outgoing links, one will be left outgoing and one will be right outgoing. So now we know what solution we start, what a directed WRAP solution is. Let's talk about how we can try to improve in those solutions. This brings us to mixed solutions. As I briefly mentioned, we will actually replace directed links by undirected links. So let's first talk about what this even means to have a mix of directed and undirected links, and then we think of them as being a solution. So here you see such a mix of directed and undirected links. So I call this a WRAP solution because for every 2-cut, you either have one directed link that's entering the 2-cut, or you have one undirected one that's crossing it. And this we call a mixed solution. So essentially just reinterpret the links same way we interpreted them beforehand in directed and undirected settings separately. So what would be a possible improving stack? So assume we start with such a non-shortenable directed WRAP solution as shown here. So we would like to exchange some of the directed links by undirected ones. So look at the green ones here. We can add to that solution. And ideally, of course, what we want to have is we would like that the green links we add are cheaper than the orange ones we're gonna remove. There's a few questions to ask here. And of course, first, how do we actually find such green links? We have to restrict our search space to make sure that we don't search over all possible solutions, which includes also the optimal solutions is an NPR problem. Moreover, we don't want to restrict it too much because we have to make sure there still is one such set we can find is improving as long as our starting solution is not already better than a factor of 2. So, and even once we have agreed on what kind of links that you'd like to add, what are the green links you want to add, there's actually more than one option to drop directed links to get a mixed solution. So here, the option I've shown here is you add the green links and drop the orange ones, but actually you could just as well have decided not to drop this one, so keep this one. Let me draw it in blue, and therefore drop that one here. This would have given a solution without that link. However, with this link here, that's also a mixed solution if you check that solution I just created here. So even if you fix a set of links you want to add, it's not unique. The decision of what you want to drop or what you can drop is not unique to different options. So if you talk about that, let's start with that question. The way we handle this is we introduce a notion of cut responsibility. So we know every 2-cut has to be covered. So what we do is for each 2-cut, given a solution, let's say a directed solution. So for every 2-cut, we define precisely, we declare one link that's entering the 2-cut to be responsible for that 2-cut. So let's look at the example here. So in this example, we have a 2-cut C. And so there are three directed links that are entering. And so each one of them is actually covering the 2-cuts, just making sure that one is fine. And so which one do we pick as the one that's responsible? So here we exploit a nice property of those non-shortenable solutions. Namely, it turns out that if you take one of those orange entering links, then if you just follow them backwards to the root along the arborescence, there's a new path to the root along the arborescence, at some point you will traverse the red link. And it turns out it's true also for the other orange one we have here. So more generally speaking, actually for any 2-cut, there's precisely one topmost entering link. And the other ones come after that link when you go from the root to those links. And so it's that topmost one that we declare to be responsible for our 2-cut. So now there's a canonical way to define a drop. The way we define it is adding, if you have a current directed solution, F arrow, and you add now an undirected link set K, then the links you're going to drop, or we're going to drop here, are precisely those directed links that have the following property that all the 2-cuts for which they were responsible are covered by the green links. And then we can drop them. Clearly, if we do things that way, we're sure that we always have a feasible mixed solution, because for every 2-cut, either the 2-cut is still entered by a directed OR, and then it's covered, or it isn't anymore entered by directed arc, but in that case, the arc got deleted. And the only reason why it got deleted is because all the two cuts it's responsible for have been covered by green edges, by green links, and therefore that cut is again covered. So what is nice about that way of deciding on how links will be dropped, if that notion of responsibility is that it is very structured, leads to several interesting structural statements. So I don't have the time to go into all of those details, but let me at least give you some ideas of the type of statements we use here. So let's try to understand or try to characterize when we can actually drop a certain link. Let's look at this bold link here from U to V. And assume we add those undirected links to our solution, to our directed solution, which you have here on the left-hand side. So I claim that those undirected links we have here, if we add them, we can actually drop that directed link. And the reason is the following. We can drop that link even though only if the following holds. If you look at the head of the link, so this would be B here, then there is a sequence of links we have, of undirected links we're adding, one having B as an endpoint, and then I can take another one that's actually geometrically crossing that one, geometrically intersecting that one, until I reach a link with one endpoint not being a descendant of B. So descendant of B in the arborescence. And that's precisely that characterization. So whenever you can find such a sequence of links, then the link of undirected link, then this directed link here can be dropped. In other words, you can look at the link intersection graph. So for each link, let's introduce a new graph. For each undirected link, we have a vertex, and two undirected links are connected in this link intersection graph, if and only if they are geometrically intersecting here or share an endpoint. So red and dark green are also connected in the link intersection graph. So in that graph here, essentially, if you just rephrase the graph here, it means that you need to have a path from one link for which one of the endpoints is V to one link, say for example the red one, where one of the endpoints is not a descendant of V. And then if this happens, you can drop the corresponding corrected link, and otherwise you can't. So now we understand how we want to drop links once we decide on what undirected link set to add. So we still have to talk about how we actually find undirected link sets to add. And the way we do this is we will restrict the class of links we're considering to add. For this, we need the notion of thin components. So what's a thin component? So here, just give you an arbitrary link, undirected link set, and I want to talk about its thinness. So this is a nice geometric interpretation, the way we define that. Namely, the thinness is defined as follows. Let's first just look at any triangulation of that cycle. And when I say triangulation, I mean that you add actually vertices, artificial vertices in fact, between the actual vertices, and you have to triangulate the area, should triangulate with respect to those black vertices. Now, given a triangulation, we can check for each line in that triangulation, for example, this one here, the total number of links of undirected links that are crossing it, that are geometrically intersecting it. So here, there are three of them, this one here, that one here, and this one here. And actually the smallest number, so here, in this case, actually the smallest, it's sort of the largest number of links that cross any such segment. And so the largest number here is 3, which means that this link set is 3 thin. So more formally speaking, the thinness is the smallest such intersection number can obtain over all triangulations. So this is actually a 3 thin link set. And this is actually connected, this notion, to the tree width in the link intersection graph. And this has also been such graphs have been intersection graphs have been studied in graph theory. And there's some nice connections there. But the notion we use here is it is by constant factor of at most a constant factor of the actual tree width, but it's more convenient for the way we use it. So now with that notion of thin link sets, we actually can can derive two key theorems. One is an optimization theorem, which says that you're actually able, for any constant, we're able to find, so any constant alpha, we're able to find, efficiently find an alpha thing link set that minimizes the ratio of the cost of the links we're adding divided by the ones we can draw. So we can, in other words, we can maximize the bang for the buck. So this shows that we can, within that class, actually find good link sets. However, we still have to show that there, as long as we have a bad solution, there actually exists a good link set to add that will make progress. And this leads to the decomposition theorem. The decomposition theorem says that for any solution, so let's just assume, just look at an optimal undirected solution shown here in green. So any such solution, any directed link set, or any directed, non-shortenable directed solution, F arrow, and any fixed constant error, you can find that there exists a partition of opt into constant thing components. The constant depends on the epsilon, such that the following holds. So here shows such a partition, such that if you look at each part in the brown, blue, and green, and check what you can draw, and then sum up the cost of those drops, then the total links you can draw is almost everything. It's up to an epsilon fraction. It's all of the cost of the directed solution. So essentially, we really can break down a full solution to smaller parts, and the smaller parts will proportionally improve on the full solution. So this leads now, this allows putting together the optimization and the decomposition theorem. You can get the first procedure that will be factor 2, a relative greedy procedure. So we start with a non-shortenable directed WRAP solution. Let's assume, so it will be called, the cost will be at most 2 or twice the cost of op. Let's assume it's precisely twice the cost of op. We really have to make an improvement to beat factor 2. And then what we'll do is we just iteratively add components using that optimization theorem. So we find a component that minimizes the cost of the component divided by what you can draw, and then replace that part and keep going. So why is it making progress? So at the beginning, we have that opt is only about twice, half of the cost of our directed solution. So by the decomposition theorem, is actually, we will have essentially bang for the buck of almost factor 2. So we will improve on that part. And this will then keep going. So the next iteration, we replace part of the directed solution. There's less left of the directed solution. Maybe then we can still improve on that part as long as that part is more expensive than not. And so those improvements, they get smaller over time, and that's also the reason why the relative greedy will stop at a certain point. And if you do the math, you get a 1 plus natural logarithm of 2 as the approximation factor. So it's a typical factor people obtain the relative greedy. And one can boost that with a local search procedure, where we actually, so that is linked to results of a prior paper of ours, the idea we use here. And the one weak spot of relative greedy is that whatever you add in the prior iteration, you don't try to improve that part in the later iteration. The analysis only tries to only checks what you can improve with respect to the original links that are left, haven't been removed yet. And one can actually improve that by also looking at local exchange steps that, if we're doing a local search procedure, it also tries to improve on those added previously. So on a high level, the idea is that the previously added links also get bidirected and then also enter the analysis in a similar way as the original links did. So let me conclude. So the main result is a 1.5+epsilon approximation for weighted connectivity augmentation. There's been a bunch of components like the directed, this idea of looking at a directed version of the problem, the notion of cut responsibility, and the notion of thin components, which then led to optimization, decomposition theorem. I skipped some main technical parts, particularly the proofs of the optimization and decomposition theorem, which are quite technical. And as I said, the different ways to then exploit those results. One easy one, just to see that we can beat factor 2 is relative greedy, but a stronger one is local search. Thanks for listening.